All right, good morning. So today is going to be lecture number 14, and we'll start off with a variation of artificial neural networks, or maybe an evolution of artificial neural networks, at least for vision, which is called convolutional neural networks. Before that, I just have one thing to address about the project. I just saw a post on Piazza about how the project, it's taking a very long time to load. I heard a couple of concerns as well on Monday as well. So we had tested this before on an Ubuntu laptop with, I believe, like a 2 GB or a 4 GB RAM, 2 GB RAM, I believe, and it was running smoothly. But of course, it depends quite a lot about the OS you're using and other factors as well, other hardware acceleration factors as well. So one thing that if you are facing this issue, then please go on Piazza on that post and let us know the time that it's taking for either loading the image or for execution of the SAM code itself. You can use something called time module, and you can use a start and an end within the time module to say which module within your code is taking a long time. If it's just reading the image, or if it's something like the execution of the SAM itself. Also, one thing I'll also be interested in is if it's a progressive issue. If the first few images are loading and executing quite fast, but it becomes slower later down the line. Because I believe what we tested on was for 100 or 150 images, but of course, many of you are doing it across like 400 images. So maybe what's happening is that the RAM is being filled. Like we are not clearing the cache, essentially, and that also might lead to this slowdown issue. So please let us know if it's either a progressive issue or individual modules, which are the ones that are having an issue. So once phase 1 is done, you'll start with phase 2, and one of the directions or track that I will give a document later down the line what exactly phase 2 will be is going to be about implementing these kind of accelerated techniques or creating these smaller versions of SAM. In that Piazza post, I linked something called Tiny SAM. That is something either you might use directly in phase 2, or it's something that you might want to implement as part of the project within phase 2 as well. But I'll talk about that down the line, like next week, and create a document essentially on what all you can do within phase 2. But if you are facing this issue, please let us know which module, the time it is taking, each step, how much time it's taking, and where the problem essentially is. Yes? Which one? Yes, it was access to CUDA. I don't know, then maybe that, it was very fast and very efficient at the time. So if you don't have access to CUDA, that is also going to create inefficiencies over there. Of course, if you do want to use CUDA and then CUDNN, then you need to have an NVIDIA GPU, which is actually more, it's for that. So I believe that if you have a laptop, like Apple laptop, you won't have access to that. Or I don't know if there are workarounds in order to get that thing. But again, there are other alternatives like Tiny SAM that we can use later down the line. All right, so that is about the project. So with that, we'll move on and talk about the main parts of the lecture today, which is about the idea of convolutional neural networks. So before I start, till this point, we have discussed about neural networks. And I want to differentiate what we had done from what we'll do today and from today onwards. And that's why I have been calling it something called ANNs, which is artificial neural networks. And the reason I use the word artificial is because I just want to use the same terminologies from now on, because what we'll be discussing today is convolutional neural networks. In the grand scheme of things, all of these are artificial neural networks. We'll discuss something called recurrent neural networks as well. Those are also artificial neural networks. Convolutional neural networks are also artificial neural networks. But just for the sake of differentiating the things we'll be discussing, we'll just make this differentiation that until today, what we discussed was ANNs, which is artificial neural networks. Today, what we'll be discussing is convolutional neural networks. If you read the literature, what we have discussed till now can come under two umbrellas. It's also MLPs, which is your multi-layer perceptrons. Again, this is a word that we had used back in lecture number, I believe it was 5, where it's a bunch of perceptrons, neurons that are stacked one on top of the other, and we just called it multi-layer perceptrons. And that is exactly the same as the ANNs that we have discussed until this stage. So what we will be discussing is a bit different, which is called convolutional neural networks. And till this point, the idea of ANNs and MLPs are very generalized. That is, you can use the same concepts. It doesn't matter what data you're using. So if you're working on something like speech data, sound, natural language processing, the ideas that we have discussed is something that is going to extend towards all these data modules. But CNNs are specifically for images, 2D and 3D videos. CNNs are designed specifically for this kind of data. Now, personally, my work has always been on images. I'm very interested in the idea of images and processing of these 2D data, and I've tried to keep that bias away. I'm pretty sure I haven't succeeded. I'm very sure that whenever I speak, the idea of images comes through. But this lecture and the next couple I'll go deep into the idea of images and image processing itself. So everything that we'll be discussing is something that is exclusively for images, and you can take small portions of that and put it onto other data modalities as well. That also means that until this point, we have discussed our X as just a bunch of features, and these features are just a vector. It's going to be different from now on, because the features of the X input to our networks is going to be an image. So it's a two-dimensional image, and two-dimensional in terms of height and width. But if it's an RGB image, then that means there'll be 3 channels. There'll be 2 dimensions and then a third dimension regarding the channels of R, G, and B itself. So this is the main difference in terms of the input that we will be discussing from today onwards. All right. So as I mentioned, so we have our input to be some kind of pixels, which is 200 cross 200. Now let's assume that we don't know we are still dealing with the ANNs, the multi-layer perceptrons that we discussed last week. So what we would do in this case is consider that to be this 200 cross 200 pixel image into a vectorized image. That's what we do, right? We always look at X as a vector. So if we want to use ANNs or our multi-layer perceptrons in this, we would vectorize this image, and it would be a column vector of 1 cross 4 times 10 to the power of 4. It's a very, very large vector that we are dealing with. Right? Your Iris dataset had just 4 features. Your California housing dataset, I believe, had around 8 features. So now what we are discussing is a very, very, very large input to the order of 10 to the power 4. What that means is that single neuron will need 10 to the power 4 weights. We discussed a part of this before last time when we discussed the difference between SVM and ANN, where if you have certain inputs, let's say x1, x2, until x10 to the power of 4. Each neuron in your hidden layer has connections to all these things. So if there's 10 to the power 4 inputs, then basically the number of weights, W1, W2, will extend to W10 to the power of 4 for a single neuron. If I need a second neuron, then again, remember, it's a matrix, right? So all the things again will be connected to the second neuron as well. So it's another 10 to the power of 4 weights. Depending on the amount of neurons you have in your hidden layer representation, your weights are going to increase. The number of parameters are going to increase quadratically. And this is an issue because for 100 neurons, this simple image of 200 cross 200 pixels, which by the way is not even your HD image that we use, 1080p image, it is not even that. It's a very small 200 cross 200 image. It's going to have 4 million parameters just for the first layer. And we already know that when we discuss these neural networks large scale, there's something called a ResNet 151 architecture where there's 151 layers that is stacked one on top of the other that we'll discuss next week. But even a single layer will have 4 million parameters if we choose to use a simple ANN, fully connected ANN in this framework. What we are missing out when we use every single element within the neurons is that the spatial correlation, we are wasting it. We are not utilizing the spatial correlation. So that brings us to the question of, okay, what is spatial correlation? So let me show this in the next slide over here. If I take this particular patch, and if I take the next patch over here, is blue visible? Yeah, I think it is visible. So if I take these two patches, they're very similar looking with each other. And this is something that we notice across all images. most of the time, there are a lot more similarities within images than there are differences. That basically means that a single patch of an image can be reconstructed based on the same basis function. So if you're familiar with the idea of signal processing, then that means that we have taken these kind of images or patches as signals, and we are saying that a same set of basis vectors, something like a cosine waves, will be able to reconstruct back these patches. A very sparse set of cosine transforms will be able to reconstruct back this image. So the idea is that we use the spatial correlation to our advantage, that we don't want to have 100 million parameters that go across the image in order to process them, but rather we utilize the spatial correlation in order to create a lesser set of parameters in our network, in our framework. So in this case, so what that basically means is that maybe there is a way where instead of a single neuron connecting every single pixel within this 200 cross 200 image, maybe there is one neuron that can work on, let's say, 8 cross 8 part of the image. That I don't need more than that within to analyze whatever is there within this neuron. And that is the idea, the main idea behind convolutional neural network, which is instead of looking at the entire input as a single vector, we look at the input as two-dimensional patches. And the hope, which is actually true, is that there's a lot more correlation between these patches. So I can reuse this neuron, even though it has been trained on a very small subset of the data, which is just this 8 cross 8 patch. I can use the same neuron across different fields, across different parts of the image, and we'll still be okay. We'll still be good with something like this. So the idea is that we'll be sharing our weights rather than having a very exclusive set of weights that is true or that is trained across the entire image. So if we do something like this, then the number of parameters will decrease quite a bit. Here, instead of doing 8 cross 8 patch, I'm looking at just a 3 cross 3. So essentially, I'm just saying that a neuron will not be looking at the entire image, but it will be looking at a much smaller portion. So let's say something like a 3 cross 3 patch, it's looking at it. So if we are discussing a vector that is looking at a 3 cross 3 patch, then basically it's 3 multiplied by 3, which is 9. I hope where the 9 is, I hope it's clear where the 9 is coming from, right? So I'm assuming that there is a 3, that the pixel values here are something like 121, 120, 125, 127, and 101, 95, 52, 200, 222, and 153. So pixel values, if you're not familiar with the idea of images, 8-bit images, basically pixel values can go from 0 to 255, with 0 being the color black and 255 being the color white, and anything in between is a grayscale. 122 is like perfect gray, and 150 is more nearer to white than it is to black, and so on. So if I'm looking at the exact pixel values here, then it'll be something like this. I'm going to take this 3 cross 3 matrix, and if I convert it into a vector, then that means that it is a 9 cross 1 vector. And that is essentially what I'm doing here. Our 3 cross 3 is going to be 9 shared weights. That's exactly what we did here as well. When we had this entire image of 200 cross 200, if we consider it into a vector, then it's going to be 10 to the power of 4 cross 1. And this is not, it's computationally very expensive and not something that we can actually utilize. So by using this idea of local connectivity, just by us saying that each patch is spatially correlated with each other and saying that neurons and the weights can be shared, we are decreasing our computation by quite a bit. So why is this good, right? As I mentioned, spatial correlation is something that exists, especially within images. Like look at, if we are, let's say our task is face recognition using images. It's very clear that even if you're using a phone, let's say not the iPhone which has the LiDAR, but a Samsung phone which is using something like face recognition in the RGB domain, it requires you to hold in front of your face at a certain distance. It's because it knows that this is how your face is going to look like, or maybe not how your face is going to look like, but this is the general area where your face is going to be, in that middle of the frame. Right? So essentially, we know that if we are doing face recognition, given this is the size of our image, then in the middle portion of it, in the center of the frame, is where your face is going to be. So we know that where the face is going to be, and this we're going to call this as inputs as are roughly registered. So if you're ever reading a paper and see the word registration, input registration, it's basically that we have a very rough idea. We have a template, an eigenvector essentially, of where we want our features to be, or where we expect our features to be. Another idea that we'll discuss later on down the line is how we can then extend this to, instead of us knowing where the features are, we know that the features will exist, but then it can be anywhere. And this idea is called spatial invariance. I'll not talk about this right now. At the end of the lecture, we have something called pooling stage, and that is where I'll talk about this. Let's just think of the spatial correlation as the first one, the local connectivity, where we know and we have access to the fact that the inputs are roughly the same. Doesn't matter if it's different faces, but the features are still going to be the same, and that is local connectivity. The next part, and this is also something I mentioned before, is the idea of stationarity. So stationarity essentially is that each patch has a specific set of features that is making it. In other words, let's look at this. Right? My drawing skills are not that good, but if I were to draw these hairs, for this particular frame, it's something like this, right? So it's like a bunch of hairs. Einstein, of course, has a very famous, the hair is very famous, so it's all over the place. But even with that, there is a specific set of weights that I can use in order to reconstruct this thing. In other words, I can take this and say that this is 0.5 multiplied by something like this, plus 0.5 multiplied by just a spatially changed version of this. So if I think of this, then if I think of this as W, then this is nothing more than W plus 1, where the plus 1 is the number of columns. It's just being shifted by a little bit, right? So if you have the same hair and the same shape, it's essentially just a bunch of shifted versions of the same weight, let's say, or let me call this a filter or a kernel. But just a bunch of shifted versions of that kernel is going to give me the hair. And all I'm doing is just adding these things, right? And hopefully this is basically what convolution is. But we'll discuss more about what this means a bit later down the line. Again, if you have taken courses in signal processing, this word is very famous, the idea of what convolution is, and it's exactly what this is. So if I have one hair as my template, I can just shift that hair in multiple places by 1 pixel in the columns, pixel within the rows, and I'll be able to say that by just adding all of these things, I'll be able to reconstruct my entire patch. But for now, even if you don't know convolution, we'll discuss more about it later down the line. But the idea is the property of stationarity, where the statistics are similar across different patches. So I can use this same hair in this patch, or I can use the same hair in this patch, like a shifted version of this. It's still the same, right? It's still the hair that is being replicated over there. So I can still use it. And this is essentially what stationarity is telling me, that most of the visual scene that you see, it's all very simple. It's all based on a very simple set of basis vectors that we can use in order to reconstruct it. So basically, this is exactly what convolution is. So we connect each neuron to an input patch. Rather than connecting each neuron to the entire image, we construct input patches. So I think I did a very, these two things, it's very far apart. In the next slide, we're just showing the same thing, but more closer together, right? So this and this are very, very similar to each other. The stationarity property between them exists. And what we can do is share weights and parameters between them. And the methodology of doing that is something called convolution with a learned set of kernels. Now, I'll be using the words kernel and filters interchangeably. So this basically comes from different communities. So if you're coming from a more mathematical perspective, if you've taken a lot more math classes, then kernels is something that you will be familiar with. If you're coming from a signal processing perspective and you've taken more classes in signal processing, then you would have heard the words filter. Both of them will be interchangeable for now. So it's the same thing. So across the lecture and even previously, whenever I've used kernel methods and stuff like that, it could have been just a filter method. It's just a filtering that we do in terms of input processing in order to get a different representation space. So for the sake of this course, these two words will be the exact same, or they will mean the exact same, which is the idea of kernels and filters. So what is different between ANNs and CNNs? So artificial neural networks, the number of parameters, we already saw this, scales quadratically with the size of the input, and the idea of stationarity or spatial correlation is not maintained within ANNs, but CNNs, which is convolutional neural networks, we connect each neuron to a patch of the input and we share their weights across different spatial locations. This is essentially the main difference between the ANNs and CNNs. Now, I want to be very clear that the idea of spatial locations is what makes CNNs very exclusively good for images. So if we are thinking about voice signals or speech signals, it's a 1D signal, it's a one-dimensional signal, and there's no, this idea of spatial correlation does not exist in terms of 2D, but it does exist in terms of 1D. Right? Whenever I'm speaking, it's not like I'm modulating my tone very, very differently, and that's why even in speech signals, there's something called the idea of windowing, and then wideband and narrowband signals that will allow me to use this, the correlation, spatial correlation in one dimension, and we'll discuss that when we talk about recurrent neural networks, RNNs, but in terms of images, there is even more correlation, not just a single one-dimensional correlation, but two-dimensional correlation, where the spatial correlation also exists, and we are utilizing that to make it, to create these CNNs, or convolutional neural networks. All right, so if you're familiar with the idea of convolutions, so one-dimensional convolution has this formula, while two-dimensional convolution has this formula, but you know, the formulas are this. I think we'll skip this slide for now and discuss the idea of convolution itself by looking at certain examples instead of just focusing on the formula part. What we are interested in, of course, is this idea of 2D convolutions, and we want discrete convolutions instead of continuous convolutions. So why discrete convolutions? So when we talk about images, right, in this particular image, if I go back here, I looked at this image and I just wrote down numbers. I wrote down 121, 125, 127, which is actually true. This is how digital images are, essentially. This is how, when you store an image in your phone, this is what is stored. It's stored in terms of the intensities of your pixels, because it's a digital photo. It's a discrete representation of the photograph or the image itself. So at every instance, each point, there's a very small point that we call a pixel, which has a certain value associated with it. And when these pixels are very small, then it might appear continuous. So whenever you see specs on your phone of 48 megapixels or 24 megapixels, 12 megapixels, it's actually talking about the number of pixels that are there in an image that is stored within your phone. More the number of pixels, that basically means that the area of, let's say, 121 here is much smaller. But of course, there's a limit to this. It's not like if you have, I don't know, like 3,000 megapixels, it's going to be better, because the human visual system cannot really differentiate between, after a certain number of pixels, it cannot differentiate. It cannot say the difference between, let's say, 121 and 122 when they are so close together, when the number of pixels are very high. So in a way, the number of pixels after a certain threshold doesn't make sense at all, and it's all going to look the same. But the thing I'm trying to talk about here is about the discreteness, that each pixel is a value, and because we have these discrete input data, the convolution that we'll be using is also discrete convolution. This slide essentially is trying to take this formula that we have here and putting it in terms of images. We'll discuss this formula in the next few slides. The takeaway from this slide should be how the image X will look. So this is essentially our input, and this is our kernel or filter or whatever you want to call it. We are thinking of this as we'll use these two things in order to create a neuron output. And that is given by this, y t1 comma t2. So this entire y will be our output at the end of the day. X is going to be our input, and W will be our kernel. This is the same W that we have been discussing till now. So whenever we say Y is equal to W transpose X plus B, this is the same W. But before we were talking about it in terms of just a vector of importance scores. But at this point, W is now a matrix, as you can see over here, of dimensions K1 cross K2. And more importantly, it's not talking about the importance but of the pixels themselves, but rather it is a kernel. It's almost like a transformation of your pixels in order to get a certain output. So usually your X will be a very large scale image, let's say 224 cross 224 cross 3. If it's 1080p pixels, of course, that's going to be 1080 multiplied by 1440. And your K, your weights in your kernel is going to be very low. In fact, I would say that the maximum you'll ever find is something like an 8 cross 8 kernel, especially if you're looking at the first layer. Later down the line, it'll be more, but in the first layer, it's just going to be a maximum of 8 cross 8, and more usually, it's going to be like a 3 cross 3 kernel. So essentially what I'm saying is that if I go back to this image, this kernel, what I'll be looking at is just a 3 cross 3 set of patches, or it's like an 8 cross 8 patch that we will be utilizing. So now I'll just talk very quickly about the idea of convolution itself. So again, if you have heard of convolution, this part should be pretty straightforward. If not, the next few slides are all going to be just about talking about what convolution is. So the way I motivated this is by saying that, let's say I have a kernel of a hair, or I have a filter of a hair. What I would do is move this hair by a certain amount, right? Let's say I move that certain amount is given by 1 pixel. So I can move by a certain pixel and process the image. I can move by another pixel and process the image. That is exactly what we will be doing. So forget about the hair part and think of it as just a filter, as just a set of discrete numbers. What I would be doing is I'm going to take this one point over here, and this is the point I'll be looking at. Given this image of size 1, 2, 3, 4, 5, 6, given this image of size 6 cross 6, I'm utilizing a kernel of size 3 cross 3. And for this element, which I'm going to call x0, comma 3, I'm going to multiply, or I'm going to apply this kernel on top of this 3 cross 3 frame within X. And each element within W will be multiplied within each element of X. And the output of that is going to go here. That is essentially what your formula is telling you. If you're going to look at an online resource, there are many cases where people will choose this as the point that you will use for convolution. Then that would basically mean A equals -1 to 1 rather than 0 to 3 minus 1. To simplify this, we are just using the top left corner here, but either of those things work. It depends on which library you'll be using, but mathematically, they will be the same thing. It's just how you're defining your elements. So let me talk a little bit more about what exactly this means. So forget the 3 reds that I have here, and let's just concentrate on the one golden point. I hope that's visible here. Yes, it is visible. So I'm talking about this point. This is the output. This is the output, and in a way what this means is that this is the output of a neuron. Let's just think of it like this for now. And if it's something like my kernel is going to be 5, 4, 3, 2, 1, 6, 7, 8, 9. Let's say this is the value of my kernel. This is something learned by using a gradient descent, but for now we don't care. We are just looking at this as a convolution operation. And at this point, you have like 150, 152, 153, 154, 155, 156, and I hope you get the drift. So essentially, we just have different pixels at these points. All we'll be doing is doing an element-wise multiplication. In other words, we'll do 150 multiplied by 5, and then 151 multiplied by 4, 152 multiplied by 3. So it's this, this, and this. And 5, 4 is, let me put a different color here. So here, here, and this 3 is here. Right? All we are doing is multiplying, and the final one is the same as well. So in this case, it will be let me call this as 160. So 160 multiplied with 9, which is essentially here and here. What we'll be doing here is just an addition later on down the line. So 150 multiplied by 5 plus 151 multiplied by 4 plus 152 multiplied by 3, and you'll get certain output. I don't know, let it be like 10,000 or like 5,000 or something like that. This will now be your output here. This is 5,000. Right? So every element is basically multiplying every element within the image. The intensity value is multiplying the kernel value itself. You're adding everything, and you're getting an output, and you're placing it within your framework. That is all convolution is doing. And that essentially is what this difficult looking equation is going to be. The sigma and sigma are, the first sigma, a equals 0 to 3 minus 1, is across the row here, and the second sigma is across the columns. So that's basically your multiplication, x of 0 plus a. A is from this point. Let me actually erase everything here to make it more clearer. A is the displacement across the rows. So if A is equal to 1, then that means we are considering this element here. If A is equal to 2, we are considering this element here. B is the displacement across the column. So if B equals 1, we are considering this element here. If B equals 2, we are considering this element here. And whenever we consider those elements, we are multiplying that X value with the W value. It's just a multiplication, which is exactly what I showed here. 150 multiplied by 5, 155, 151 multiplied by 4, and so on. So this equation is nothing more than just a bunch of multiplications and additions that are done together using my kernel and my image. And I can now do this across different paths. So here you see that I was looking at this pixel over here. This was my, let's call it our main pixel, our main element, and that will be our output for this main element. Now, if I'm using this pixel here, then this will be the element that I will be generating, essentially, right? If I use the last one over here, then this is the one that I will be generating. Yes, question? Can you repeat that question, sorry? Yes. So you're saying, what if instead of 6 by 6, it was 4 by 4? Oh, okay. Okay, I understand. So let's say my initial is green, and probably is not visible. Let's say my initial is this element here. So let this be some element. So I'm just replicating this 4 by 4 here. So this is this element here. Now that means that the element, the kernel I've taken is something like this, right? In the next stage, I will move this by 1. So this would be y of 0, 0 in my example. I'll move this by 1 and take this. Sorry, you can't see that. So I'll take this as my second example. So my kernel here is something like this. And the output I get is this. So it's y0, 1. Same thing, I will use this. So I'll get this output here. And finally, I'll use, let me use black here for this. And the output I get is this. So now I've covered the entire image. Yeah, it's basically just sliding across different things. And now I have this kind of a 4 by 4 matrix, which is your y. Yes, every single element, the sum and the multiplication of it. No, just 1 times 1. So yeah, if this was 151, it's just multiplying just whatever was here and so on, and it's an addition of all those things. Yeah. Yes. At this point, it's not a compression. Actually, yes, maybe at this point you might think it's a compression because we are reducing it, but I'll show you that this is only for one, what we would call a channel, but that could be more convolutional kernels that we can use. In fact, what you will notice in like real-world CNN architectures is that you're in fact increasing it. Your size is now increasing within the framework. So I wouldn't call it a compression for now, but there's something that we'll discuss down the line called pooling, which will do what you're saying, which is doing a bit of compression. All right, so yes, sorry, question? No, that is something called a stride, which we'll discuss down the line. You don't need to do it per pixel because we discussed this, right? So the intuition is, of course, that anything that is just 1 pixel down the line is still going to be very similar. So maybe you really don't need that just 1 pixel. You maybe need a higher amount of what we would call strides. So it's not a requirement. Of course, if we are just discussing convolution, then it is this kind of a, you can just do it as 2 multiplied by a and 2 multiplied by b, which is going to give you a different stride within the framework. I'll talk about it. I have slides for strides. Yes.
When we talk about the stationarity, where there's certain aspects of the picture that are similar to other aspects of the picture,
Mm-hmm.
I'd assume for a lot of images, you might not find 3 by 3 matrices that are exactly the same grayscale values.
Mm-hmm.
So is this type of convolution estimating similarities that are lossy, or do they match them exactly?
They don't match them exactly. They are trying to find, the way you said it was they have like a lossy version of the patch that exists. And the way we overcome that is by having multiple kernels. And multiple kernels, what happens down the line is we'll add another layer. So the outputs of these kernels will then be added together and you'll get another output. So that's why we stack layers one on top of the other and we'll get our results. You'll never get the exact pixels back in your kernels. It's just that it's a mathematical function that at the end of the day, we'll get back the patches together. All right, so essentially what we are doing is just a bunch of multiplications and additions. So in this case, if our kernel was 0, 1, 2, 2, 2, 0, 0, 1, 2, all we are doing is 3 multiplied by 0, 3 multiplied by 1, 2 multiplied by 2, 0 multiplied by 2. Maybe I can show this here. So 12 is given by 3 multiplied by 0 plus 3 multiplied by 1 plus 2 multiplied by 2 plus 0 multiplied by 2 plus 0 multiplied by 2, 1 multiplied by 0, 3 multiplied by 0, 1 into 1, and 2 into 2. All of this should give us our 12. So 12 is coming from this, and 3 multiplied by 0 is coming from this, 3 multiplied by 1 is coming from this, 2 multiplied by 2 is coming from this, and so on. The value of 2 itself is the pixel value within your image, and the value of 2 is given by this kernel value at this element. Now, if you want to now shift to 12 for the next y2, then basically you'll be using the kernel on this part of the image. That's it. It's just a bunch of multiplications and additions, and once you do that, you shift it and you find your solutions. So of course, as I mentioned, kernels is equal to filters. We'll be using these terms interchangeably. From now, we'll discuss something called a convolution layer. Until this point, it was more just convolution, but convolution layer is exactly the same thing. It's utilizing the local connectivity, parameter sharing, and spatial arrangement within the framework. So when we talk about convolution layer, we are talking about this thing. So whenever you read some papers, or if you just type in a CNN, you'll see these kind of blocks that are there. All we are discussing there is just this kind of layer. So my input, let's say I have CIFAR10C, CIFAR10 as my data set I'm using. In CIFAR10, maybe you've already seen this, and we have discussed just this before, but the inputs are of size 32 cross 32 cross 3. And the way we usually represent it is by this cuboid function. 32 cross 32 is the height and width, and the depth is given by 3 here. This is our input. We now pass this through a kernel. And this kernel, let's say before we were talking about 3 cross 3, but now of course we are discussing an image, an RGB image, which has channel depth of 3. So now we'll have 5 cross 5 cross 3. So the height and width before what we had before, instead of 3 cross 3, we now have 5 cross 5. 3 is for the channels, number of channels, the R, G, and B. So it's exactly the same thing. Instead of looking at it as a 2-dimensional area, we are now looking at it as a volume, a 3-dimensional volume. So 5 cross 5 cross 3. So the idea is that the filter with the image, we slide over the image spatially, computing these kind of dot products. So everything we have done is just basically just a bunch of dot products, which is just multiplying the elements and just adding those values in order to get your output, right? So a collection of 3 unique 2-dimensional filters of dimension 5 cross 5. There's 2 ways to look at this 5 cross 5 cross 3. You can think of it as a volume, a 3D volume, or more importantly, the way we usually look at this is that it's 3 unique 2-dimensional filters of 5 cross 5. The reason is that whenever we say a 3D CNN, we are discussing it from a video perspective. So if you read a paper and they mention that they're using a 3D CNN, then that means they're looking at a 4-dimensional input where there is a time axis as well. So we shouldn't be confused. Whenever it's a 3D CNN, it's basically for a video with a 4th dimension of time, because whenever we discuss about these kernels, instead of thinking it as 5 cross 5 cross 3 kernel, we think of it as 3 unique kernels of 5 cross 5. That is, we think of it as 3 unique kernels of a 2-dimensional kernel, in this case, size 5 cross 5. So the output, again, it's exactly what we discussed, a multiplication plus addition together, and this could also be considered as W transpose X. So just the idea of convolution is W transpose X, and once this convolution is made, you can have a bias term that can be attached to it. Of course, as we have already seen, this bias may not be required. You can just increase your input dimension by 1, and you learn your bias within your weight structure itself. So it's a vectorized version. It's not as important, but essentially it's similar to what we have done before. So each convolution is in fact just a linear line that we are learning regarding the input. Now, let's say we have done this 5 cross 5 cross 3. So if I go back here to the convolution we were doing before, a 6 cross 6 element that was multiplied using a 3 cross 3, that was convolved using a 3 cross 3 weight, was giving you this 4 cross 4 output, right? Every time we just moved it by 1 stride, we used to get this 4 cross 4 map. Within neural networks, this part here is something called an activation or a feature map. Whenever you see the words activations or a feature map, it's basically the output of image and being convolved with a kernel. That is essentially what we'll be discussing, what we'll be talking about whenever we say the words activation or feature map. This is the output. If this is 6 cross 6 before, this is going to be 4 cross 4. Just the output of that is called the feature map or the activation map. We of course convolve over all spatial locations in order to get this result. Now, as I mentioned before, we're not limited to just using one kernel. We can use more kernels. So instead of just using one 3 cross 3 cross kernel, we can also have, sorry, I'm using 5 cross 5 here. So let me use the same terminologies. So instead of having a 5 cross 5 cross 5 kernel, I can have 2 5 cross 5 cross 5 kernels, right? And the output of these 2 5 cross 5 cross 5 kernels are 5 cross 5 cross 3 kernels will give me 2 separate outputs. They're not together. So I use this one kernel to spatially convolve throughout the image, and I get this kernel. And I take the next kernel, which will give me this output. And these two are separate feature maps. Now I have two activations, or two feature maps, based on the kernels that I have chosen in order to do it. And generally, you don't find one or two kernels. You'll find a lot more kernels in your convolutional neural networks. In this case, let's say if I have 6 filters or 6 kernels, my output is going to be 28 cross 28 cross 6. Each kernel will convolve over the input to give me separate activation maps. In this case, the blue is associated, the first blue, the yellow is associated with maybe the color combination. Color coding is not correct here. The second one will be here, third one will be here, and so on. What I'm trying to say here is that all of them are separate. They don't mix together at this particular stage. The outputs of a kernel are independent of each other, and you'll get separate activation or feature maps. So the spatial arrangement, we'll look a little bit more regarding the dimensionality itself. So let's start by thinking of a 7 cross 7 input and a 3 cross 3 filter. Of course, the 3 channels is still there, but we are just looking at a single channel and how it is going to look like. The output from this is going to be 1 point. I'll move over 1, and I'll now get my second point across the same 3 cross 3 filter. I'll move over another one, and I'll get here, fourth one, and fifth one, right? This is exactly like we saw before. So all we are doing is now we have been displacing in the A dimension within that formula. A goes from 0 to, let's say, 7 minus 1, or how much ever that is, and we are basically doing that dimension displacement. At every point, we are getting our, not this one. At every point, we are getting some convolution output that is giving us these kind of regions. So the same thing, if I do it across different columns as well, I'm going to get my 5 cross 5 output, and this is basically my feature map. Right? Hopefully this is clear. A 7 cross 7 input given a 3 cross 3 filter is going to give me a 5 cross 5 output in this particular case. Now, let's say that we discussed this before. The question was, I'm not interested in moving one element after the other. So in this case, you're seeing that there is just one displacement element. In many cases, one displacement maybe is not as helpful because your spatial correlation is going to exist quite a bit. So maybe you're not that interested in just a single displacement. That is something called stride. The word that we use when we don't want a displacement to be just one, the displacement itself we are going to call something like stride. So in the previous case, our stride was just 1. So let's say that I want my stride to be 2. What happens then is that you'll move twice. So before you would have noticed that this portion was also covered by the kernel. Now it is not. Your stride is essentially 2, and you're moving by 2 dimensions, or 2 outputs in this case. So if you actually do the convolution, what you'll see is you'll get 2 outputs here, and the next one will be at the very end, and you'll already be done with your image in these 3 pixels, or these 3 displacements. So the same thing at the bottom as well. So you can move 2 strides within the columns, and finally your output is now a 3 cross 3. Remember, before a 7 cross 7 image with a 3 cross 3 kernel, stride 1 was giving you 5 cross 5 output. Right now, a 7 cross 7 image with a 3 cross 3 kernel with stride 2 is giving you a 3 cross 3 output, right? So just remember these things. Now, let's say that I want my stride to be even more. Instead of having just as a stride 2, I want stride 3. So what happens is now you will move this entire framework by 3 times. So it's going to be something like this. There won't be any overlap between the previous image and the current previous patch that you're looking at and the current patch. So the problem is it doesn't fit, right? So before, everything was very nice. So as soon as you finish 2 strides, so let's take the stride 2 case. In this case, we move by 2 here and move by another 2. And we kind of completed our image, and we got this 3 cross 3 as our output. But if I want my stride to be 3, I can't do it, because the first stride will work, of course, but the second time I do it, it is going to be something like this. And there is no input at this point, right? We don't have any kind of an input when there is stride 3. So our stride 3, we cannot apply like a 3 cross 3 filter on 7 cross 7 input with stride 3 in this case. So the way we can calculate strides, if it's possible or not, in just this simple case, is by this formula. Output size is always going to be p minus k divided by number of stride plus 1. So in this case, the kernels that we have been looking at is 3. The input size that we are looking at has been 7. So 7 minus 3 by 1 plus 1. So this is going to be, remember, the first one was 5 cross 5, right? So that is what the output is. 7 minus 1, which is 4, divided by 1, which is 4, plus 1 is 5. Now, in the case of stride 2, 7 minus 3, which is 4, divided by 2, which is 2, plus 1, which is, we got a 3 cross 3 as our output. Question, yes? Yes, they wouldn't overlap. Yeah. Not really. So yeah, convolution, it does need something of a overlap, but maybe the spatial correlation is so different between all of them that the convolution on the same patches may not make too much sense. But again, it's completely dependent on the data and the application that we are doing. So for instance, if something like if your kernel itself is 8 cross 8, then I would say you need a large overlap. But if your kernel size is like a 3 cross 3 or a 2 cross 2, then really there's not as much overlap that is required in this framework. So it also depends on the size of the kernel and the kind of input that you're looking at. Yes? No, it can. Next slide I show how it can be. But I'm just motivating how it can be bigger in this particular case. Yes, question? Yeah, the next slide is padding. So yes. So again, if you're familiar with the idea of convolution and signal processing, we have something called zero padding, and there's many kind of paddings involved. So we can solve this basically, but I'm trying to motivate that part by showing that if you have stride 3, 7 minus 3 by 3, which is 4 by 3 plus 1, so it's 1.33 plus 1. So it's not a discrete size here, right? So stride is a discrete value. You can move by 1 pixel or 2 pixels or by 3 pixels, but you can't move by 2.33 pixels. That is not realistic. So the way we overcome it is by something called zero padding. Basically, instead of just looking at it as a 7 by 7, I pad zeros on this side and I pad zeros on this side, up top and bottom as well. I think in this case it's 1, 2, 3, 4, 5, 6. So it's 6 cross 6. Now I'm just padding on the left and the right, and essentially I have 8 as my input, right? So again, zero padding is something that can be done. There are other kinds of padding as well. You can just replicate this. So instead of this being 0 here, it could have been 2. This also could have been 2. This could have been 2. This could have been 3. So I'm just padding whatever is here, essentially. I could do that as well. Or the most simplistic case is I'm just padding zeros across the entire framework. And if I do that, in this case, I will get a solution which is not, it doesn't have to be like it can be a discrete pixel, the amount of strides that is possible. So I can zero pad, across different ways. So in this particular case, if my input is 7 cross 7, then I can zero pad in different ways and I'll be able to get it. So if I draw the thing here, the stride 3, and here, so I now have access to all results, right? I'll be able to get my solution in this particular case. So that brings us to, again, the goal that we are talking right now is talking about the idea of dimensions of what my convolution layers has to be. So my input is, let's say, an image. It's given to us, which is 32 cross 32 cross 3. Let's say I'm using 10 filters, 5 cross 5 filters with stride 1 and pad 2. My output size is going to be given by this particular formula. 32 plus 2 into 2 minus 5 by 1 plus 1. So which basically is your input size plus 2 into padding minus your filter size divided by stride plus 1. Again, this is very similar to what we were doing before, p minus k by stride plus 1, except now we are multiplying this by the padding as well. We're multiplying the k with the padding part. I hope the output size is clear. It's just the same math that now moves with the zero padding part as well. So what this size means is essentially we are calculating our parameters. So instead of 10 to the power 4 parameters, now we are reducing it by a lot, right? So in this case, my number of parameters in this layer is going to be, for a particular kernel, it's going to be 76, 5 into 5 into 3 plus 1, and the output as well. 1 is for bias over here, and if I have 10 filters, then it's going to be 76 multiplied by 10, which is going to be 760 parameters. So if I were to represent this in, let's say, PyTorch or TensorFlow, then the way you would have to input your elements is by this. So your input is going to be n, number of channels, which is going to be 3. The number of images itself. So, okay, maybe this is not something I should talk about now. The first one, it's something called batch size, which is the number of samples that you'll input into your PyTorch. The second one, Cn, is the number of channels, which is going to be 3. Your height and width is going to be 32 cross 32 for Cypher 10. Forget the n for now. We'll discuss this more, I think, next Wednesday when we talk about the idea of training these CNN architectures. Same thing with kernels is going to be Cout, which is the number of outputs that you need from your kernel. Your Cin, the number of channels that you're taking in. Your K0, K1 is just 3 cross 3, 5 cross 5, whichever kernel you want. And the output, of course, is going to be the output here. So the same thing is represented in the diagram over here. One additional thing is sometimes, you don't have to calculate all the time. Whenever you're using input into these libraries, you don't have to calculate, oh, I need to do this amount of padding, I need to do that amount of padding, and so on. So what happens is you can use a ceil function or I believe it's a floor function that we use in PyTorch, where if it's something like a 2.33, it kind of takes the integer that is below it. So it takes 2 as the number of padding required or anything in order to get your solution. So hout and wout will be a floor operation on your framework. So everything that we have looked until this point is the idea of a convolution layer. So a convolution layer is a kernel that is replicated with the number of kernels. Yes, question? Yes. Top, bottom, left, and right. So all of them. So the idea of a convolution layer is just this. A bunch of kernels stacked on top of each other, all of which convolve on the input in order to, or all of which convolve on whatever input is coming in order to give you a certain output. This is what we would call a convolution layer. Now, a convolution neural network is, you can think of it as just a bunch of convolution layers that are stacked one on top of the other. Because until this point, we discussed artificial neural networks, which are like neurons in one layer, and these layers are now stacked one on top of the other, right? CNNs are exactly the same thing. You have these convolution layers that are now stacked one on top of the other. So in this case, you have 32 cross 32 cross 3. You have certain kernels, 5 cross 5 cross 3 kernels. The intermediate feature map is going to be 28 cross 28 cross 6, because you have 6 kernels here to begin with, and you're using this as now an input to a second convolution layer. Right? So previously you had a 5 cross 3 filters with stride 1 and 6 of them in order to get 28 cross 3, which are our feature maps. These feature maps are now the input to the next layer, and the next layer will be 5 cross 6 kernels. 6 because this is the number of outputs that you had from the previous one, and that came because of the 6 filters that you had in the first layer. So this are now our filters. With stride 1 is going to give us a 24 cross 10 output, right? So you might think that the height and weight, height and width are decreasing from 32 to 28 to 24, but the number of layers, channels are increasing. So it started off with 3, it was 6, and now it's going to be 10, right? So going back to your question about is it a compression, it's not. I wouldn't call it a compression at this point. It's just that the way we are looking at our input is changing based on the number of channels and kernels that we have access to. But essentially, the goal here is that given this input, we are constructing a feature map. This feature map will be input to another set of convolution layers, which will give us a separate output. And all of these are kind of taken together in order to construct your convolution neural networks. And this is the main difference. So fully connected networks is what we saw last time, where every single element within your input was connected to every single neuron. But in convolution layers, it's not like that. You have your entire input is going to multiply with a specific set of kernels in order to give your output. The number of parameters are going to be very less, but in a fully connected network, what happens is all these elements will give you a single number, right? That's how 10 power 4 parameters work. But then in this case, we are increasing our computation. That means that we are increasing our number of multiplications and additions that are required. But in the process, we are reducing the number of parameters that are required. So it's kind of a trade-off. More computations, but less number of parameters in order to achieve the same thing. Now, I say less parameters, but again, I've already talked about this before, but the newer architectures, the GPT-4, for instance, has 1.76 trillion parameters. So just imagine the number of computations that are required in order to give one output. All right, so we'll be thinking of this from a receptive field perspective. So the next slide basically explains what that receptive field is. So given this input of 5 cross 5, each kernel will multiply and add within this small patch, right? So this green patch here is looking at this 3 cross 3 patch that exists. But now, if I put another convolution layer on top of it, of a 3 cross 3 patch here again, it is basically looking at this 4 cross 4 patch here, because this element comes from somewhere like this. Actually, maybe not a 4 cross 4. It's looking at the entire 5 cross 5 patch, right? So the receptive field of your layer number 3 is going to be greater than your layer number 2. In other words, what I'm saying is that in your first layer, you only have access to small patches of your input. Your output is a function of a 3 cross 3 patch within your input image. But my second layer, or in this case, my third layer, is going to consider not just that 3 cross 3 patch, but it's going to consider like these patch here in the previous input, which in fact has come from the entire 5 cross 5 patch. So in a way, you're replicating your fully connected layer, so your fully connected network. Right? Your fully connected network in the beginning, every single pixel was connected to this kind of W in order to get a certain output. But now, since we are stacking one layer on the other, and we're using them as inputs, the activation maps as inputs, your receptive field of this is the entire 5 cross 5 image. And that's true for everything. So you've been looking at different ways of representing the same 5 cross 5 image in this kind of a 5 cross 5 activation map or a feature map. So that's the good thing about convolution neural networks. By having multiple hidden layers or stacking layers on one on top of the other, as and when you come towards the end of your architecture, you have looked at the entire input image, not just a small patch. And that is what we call a receptive field for a particular neuron. Question? No, it does not. That's a difficult question to answer. I think that is dependent on the architecture. But in general, at least initially when convolutional neural networks was constructed, it did keep on increasing. And I'm assuming that you mean the 6, 10, it increases, right? Yes, I think the first architecture, which was first big architecture, which was AlexNet back in 2012, ended with 256 or 512 kernels. I don't remember. So the number of kernels did keep increasing, but this has not been the case for the last few years. It does keep on decreasing after a while. Maybe a good way of representing it is if you see research papers, the way they show architectures is something like this. So you have this kind of a large height and width and small depth, but the next one is going to be something like this, where the height and width decreases. So your 28 cross 28 is less than 32 cross 32, but the channels increase, so it's becoming a wider cuboid. And the next one is going to be even higher. The number of channels would have increased, but your height and width has decreased. So if you ever see a research paper where they show your architecture, it looks something like this, which means that your height and width was very big to start off with, but number of channels was less, and it becomes opposite as and when you move forward. Yes, question? The number of channels that I'll be using. So the reason I need a higher number of channels down the line is because I want to have a receptive field that is looking at the entire image. right? In the beginning, if I'm just using a 3x3 kernel, it's just looking at a single patch. As and when I move forward, my kernels are looking at bigger patches. So the second, in this particular layer, it's looking at the outputs from this entire thing. This here is a, maybe I'll remove all the colors first and then discuss. So the first green thing I hope is straightforward. It's looking at this particular patch here. But the second one here is dependent on this patch, right? So in my next layer, in this particular layer, when I am utilizing this thing, this entire thing, that means I am looking at both the green patch as well as the red patch. Both of them together, this is a combination of green plus your red. And it's of this black as well. Right? So this element here is of this black. So I'm utilizing all three in order to construct this one patch. Same thing here at the bottom as well. So essentially, this one element here is looking at the entire image. So you need more of these kernels, which is looking at the entire image at the later stages than you need in the initial stages. In the initial stages, we'll see this during visualization process when we talk about explainability in neural networks, but at least in images, the first few things are looking at very low-level features like edges. But as and when you come to the later stages, it starts creating objects. It starts creating, I don't know, if you're looking at something like object detection, this element is looking at, let's say, like a cup, versus this is looking something like a bowl, and so on. So you'll see that what activates these regions, the features, is more bigger semantically accurate images. Yeah.
Why would the depth be greater than 1? Because that
yellow highlighted square is just one number, but if I go back to this particular thing here, so you see the 24 cross 24 cross 10. So there'll be 10 different channels. So even though I'm talking about this for one channel, there'll be more channels. My point here is that you need more number of these channels and outputs and later down the line, because in the beginning, it's looking at all edges. This will be, again, clearer when we talk about explainability, but the first layer is only looking at edges. And how many edges can there be? This. So this are, let's say, 5 kernels, right? These 5 kernels can look at, can recreate all image patches, like a very simple 3x3 patch. It can recreate all these patches that can exist. But as you come to the later stages, you have this semantically different objects is very large. Like you can come up with a cup, a bowl, an animal like a dog, all these breeds. So you need more activations and channels as you come later down the line, because it's looking at objects rather than simple like edges or these kind of things. Yes. So output channels of a convolution, yes, you derive it based on the input channels that exist. But in the beginning, I'm sorry, I'm not sure what you mean by the question. So if you're initializing a neural network, then you decide that this is the number of output channels I require from my convolution layer. So initially, Cin is always going to be 3. If you're looking at an RGB image. If you're looking at a grayscale image, Cin is always going to be 1. But then you can decide that Cout can be 6, or you can decide that Cout can be 10. And whenever we say that neural networks are a little bit hard in terms of assigning the number of parameters, it is because of this issue. It's not always clear that I need to use how many channels I need to use or how many neurons I need to use within a particular channel. But whenever you're coding, you do need to specify the number of output channels yourself. Initially, I think it's a good practice to start by increasing it, yes. Again, next Wednesday, we'll talk about like tips and tricks on how to do CNN training architectures and stuff like that. There we'll see exactly how we have developed an intuition for looking at the number of channels and so on. All right, so when we talk about CNNs, we have only discussed the first part, which is convolution. This is from AlexNet, by the way, this architecture. This was back in 2011 when there was something called ImageNet ILSI SRBC challenge, which is given a million images, you need to learn on million images, and based on 1,000 categories or classes, you need to classify your images. And until 2010, it was all about SVMs, deformable part models, and so on. And the first neural network that won this challenge was something called AlexNet in 2011. There was a night and day difference between the error rates between something like AlexNet and before. So that started this kind of a deep learning trend or a revolution, you might say. And the idea in that case was that we had a bunch of these convolution layers stacked one on top of the other. And there was two other things that we haven't talked about, which is the idea of pooling and then this kind of output. So I don't know how much we'll be able to complete today, but maybe we can complete the pooling part today. So, you have your feature maps, which are the outputs from your convolution and RALU. And then we have other stages as well, which is your pooling stage. So let's talk about, so we finished this. Now, within this, we finished the convolution layer. And we have two things, which is the pooling layer and something called the, this is easier, the fully connected layer. So just FYI, so I think I had it open here. Yes, if you want to construct these neural networks on PyTorch, you can just Google simple MNIST PyTorch example, and PyTorch they've given a lot of these kind of, I don't think I can use, sorry. So, so PyTorch has given a lot of examples. We'll discuss everything that exists within this program like Monday, and by Monday, Wednesday, we'll be done. But essentially, look at the first two modules over here, which is going to be very important. Our forward, which is called our forward propagation, is a bunch of convolution layers with activation functions. And the activations we generally use these days is an ReLU or ReLU function. Then we have max pooling. Dropout, we'll discuss what that means on Monday. Pooling, hopefully I'll finish today. The flatten, FC1 means a fully connected layer. ReLU, dropout 2, and fully connected 2 as well. So essentially, that is the architecture. If I want to create an architecture within PyTorch, you really don't need to code anything. Everything exists. There are modules, nn.modules, that you can use in order to construct these modules within PyTorch. It's a very good library that you can leverage in order to construct these architectures. So whenever you see these architectures in research papers, it's just those lines in terms of coding, in terms of creating the architectures. It's a very easy way to create whichever architecture you want within PyTorch. All right. So the idea of pooling is very simple. Our goal is, given a certain feature, let's say we want an eye detector within this image. Our goal, it doesn't matter where this eye is in all these patches. We want to know where the eye is. We want to know that if an eye exists or does not exist, right? So let's say my kernel, 3x3 kernel, is an eye. Maybe this is atrocious drawing, but basically this is the eye. This is how my kernel is looking like. Let's say this is an 8x8 kernel with these pixels. So that would mean that this is 1, 1, 1, 1, 1, 1 in most cases. And in this case, there'll be 0 and 0, right? So I'm just constructing an eye kernel, and I'm using this to convolve across the image, the Einstein image I have over here. So the output is going to be just a correlation. So all we are doing is convolution, right? And convolution is nothing more than just multiplication and addition. So when I, in the image, IM multiplies with the, actually this should have been I within the image multiplies the I within the kernel. Essentially what you'll have here is an autocorrelation rather than correlation, which means that that is the highest number that you are going to get. So if your goal is for an eye detector, all these other elements don't matter to you. Only thing that matters is the highest element, the one that is giving you this kind of an autocorrelation function. That is essentially what max pooling is. It just takes the maximum element within your activation map and it uses that. So by pooling filter responses at different locations, we gain robustness to the exact spatial location of features. So if my feature that I require, my kernel is as an eye, I'm just going to look at all the features that exists, and I'm going to give, I'm going to take the maximum output within my activation map. that is going to be my filter. So that is what we essentially call max pooling. So why do we do max pooling? One, it makes the activation map smaller and more manageable. And more importantly, it gives the spatial invariance. Many times we just want a kernel to be looking at the eyes to detect if there are eyes, and it does that quite well. By using a max pooling framework, I'm discarding all the outputs that I don't need, and I'm only utilizing those outputs where I know that in this space there is an eye, which is max pooling. Max pooling is the most famous kind of pooling. So in this case, if I have 1, 3, 2, 9, I'm using a 2x2 pooling. I'm just looking at the maximum over here, which is 9. But there are other kinds as well, average and L2 pooling. When your kernel is very small, average pooling might make more sense. But in most cases, especially in deep learning, we always utilize the idea of max pooling. So hopefully the max pooling itself is clear. In this red region, 9 is the highest. Green region, 2 is the highest. Here, 6 is the highest, and here, 3 is the highest. So we're just selecting the highest activations within a particular region, and that region is decided by this 2x2 pooling function. And this here gives you the receptive field. Now, pool size plus k minus 1. So the output has now been reduced a little bit further, which is given by this pool size plus k minus 1. So that is about the pooling thing. So that will be the end for today. From next Monday, we'll start back with the fully connected layers. Thank you.